Hello everyone, welcome to the Biochemia web channel. I'm here with the topic titled Isomerism and Stereochemistry in Organic Compounds. Do not forget to like the video to reach more people. I wish it to be useful. Let's start. The contents of the topic are: firstly, I will introduce you the isomerism, some definitions, and then continue on types of isomerism. And there are two class of isomers. The one is constitutional isomers, and under this title, we will discuss skeletal, functional, positional isomers and tautomers. And the second class of isomers are stereoisomers, which will constitute the majority of the topic for today. And we will discuss chiral and achiral molecules, Stereogenic Centres, Cis-Trans Isomers, Enantiomers, and etc. Isomerism is the first concept we come across when we examine the placement of molecules in space. Thus, we define isomers as there are different compounds with the same molecular formula, and iso means same. These are compounds with the same molecular formula but different arrangement of atoms. Isomers is briefly defined as compounds with the same closed formula but different open formula. As I said in the content slide, there are two major classes of isomers: constitutional isomers and stereoisomers. Constitutional or structural isomers differ in the way the atoms are connected to each other. Stereoisomers differ only in the way atoms are oriented in space. Stereoisomers have identical UPAC names, except for a prefix like cis or trans, because they differ only in the three-dimensional arrangement of atoms. Stereoisomers always have the same functional groups, but in constitutional isomers, it varies. And the particular three-dimensional arrangement is called a configuration. The stereoisomers differ in configuration. The cis and trans isomers and biomolecules, starch and cellulose, are two examples of stereoisomers. And please don't forget, in stereoisomers, they have the same functional groups. And here is two basic examples comparing constitutional isomers and stereoisomers. And look at the constitutional isomers firstly, and as you see, they got closed formulas. They have the same number of carbon and hydrogen atoms. But when we open the molecule completely to check the arrangement of atoms and especially the bonding patterns of atoms, we see the methyl group in this isomer attached to the second carbon atom, but here it is attached to the third carbon atom. Thus, as you see, despite having the same molecular formula, same close formula, they have different names and also they have different features. This is the constitutional isomers. And in stereoisomers, as in the constitutional isomers, they carry the same number of carbon atom and hydrogen atom. When we look at the bonding pattern, they have the same bonding pattern, but different configuration, different arrangement of atoms in space. And in this isomer, the both methyl group attached to the same direction, close to us. These bold lines represent it close to us in two-dimensional. Think about this in 3D. But here, as you see, the dot lines, which means this methyl group, this configuration is towards us. Think about this is close to us. This is the back of the molecule, or in here, both are on the front of the molecule close to us. And they have the same molecular formula. They have the same naming, as you see, 1,2-dimethyl cyclopentane, except the prefix. This is cis and trans. This is the stereoisomers. Stereochemistry is the three-dimensional structure of a molecule. This is a discipline. This is a science branch focusing on the three-dimensional structures of molecules. It investigates how atoms are arranged relative to each other in a molecule in space. How important is stereochemistry to biomolecules? Think about this starch and cellulose. Illustrate how apparently many differences in structure can result in vastly different properties. Starch and cellulose are two polymers that belong to the family of biomolecules called carbohydrates. And as a definition, a polymer is a large molecule composed of repeating smaller units, which we call them monomers, that are covalently bonded together. And when we look at the monomers of starch and cellulose, they are same. They consist of glucose. But how the same monomer produce different polymers? It relies on stereochemistry. And look at here the difference of cellulose and starch, which they have the building blocks of glucose molecules, and these are each are glucose molecules, but they form a covalent bond in different arrangement. In the cellulose, both bonding, and as you see, there is an oxygen attached to glucose, and here another glucose. So I'm trying to explain simply that we will discuss deeply in biochemistry topics, because this is a glycosidic bond, which is occurred between the aldehyde group of one glucose to the alcoholic group of another glucose. Also, it's a kind of ether bond. It forms a full acetal. And the bonding pattern in both sides, as you see, in equatorial. Thus, we have a two equatorial bonds which provide the molecule to be in a linear shape. What about in starch? What happens in starch? As you see, one bonding occurs in an axial orientation, and the other here occurs in an equatorial orientation. Thus, we have a one axial and a one equatorial bonding, which forms a band at the point of bond formation. Thus, when we look at the starch, there is always bands, and it provides a spiral-like shape for the starch. So they have very different molecular shapes due to stereochemistry and due to the bonding patterns, due to the arrangement of atoms. Let's start with constitutional isomers. Constitutional isomers, sometimes we also call structural isomers, differ in the way the atoms are connected to each other. Thus, they have different UPAC names. Do you remember the UPAC? Yes, I hear that you say, yes, we are remember. It's the International Union of Pure and Applied Chemistry. The same or different functional groups, different physical properties, and different chemical properties. And as we did in the previous slides, a good example here, 6 carbon atoms and 14 hydrogen atoms can arrange to provide two different structural isomers. As you see, 2-methylpentane and 3-methylpentane. Same molecular formula, but different names. There are three types of constitutional isomers, and the one is skeletal isomers that they have the same functional groups. They have the same functional groups but differ from each other in the connectivity of the carbon skeleton. as I gave an example for 2-methyl and 3-methyl pentane in the previous slides. They are the skeletal isomers. Functional isomers, they have different functional groups. This is important. They have different functional groups. They carry the same number of atoms, but when we look at the open formula or the exact molecular formula, how the atoms bonded to each other, we will see a different functional groups. And this third type is the positional isomers. They are the constitutional isomers sharing identical carbon skeletons and functional groups, but they distinguish themselves by the specific arrangement of these functional groups along or within the carbon chain. Shortly, this means that the functional group is at the different position when we compare two isomers. This is why we call it the positional isomers. And let's look at some examples. Yes, we have an example here, the butane and the 2-methyl propane. And I give you 10 seconds to think about whether this is a skeletal, positional, or functional. And yes, the time is over. So, firstly, in studying the isomers, firstly, we have to be sure that the given two molecules are isomers. And to do it, let's count the number of each atom. And here you see there are 4 carbon atoms. Also in this molecule, there are 4 carbon atoms. And there are 10 hydrogen atoms in the butane and also in methylpropane. Count the number of hydrogen atoms. And you will find that there are 10 hydrogen atoms. So this is the C4H10. Here also C4 and H10. Thus, as an initial approach, we are now sure that these two given molecules are isomers. And then continue on identifying their type of isomers. And as you see, they are constitutional isomers because they have different bonding pattern. In butane, linear structure, but in here in methylpropane, we have a substituent. This is a substituent attached to a 3-carbon backbone. Let me erase to make it more clear. Now we understand they are isomers and they are constitutional isomers. One type of, they are the skeletal isomers because they have different carbon skeletons. This is a 4-carbon skeleton. There is a 3-carbon skeleton carrying a 1-carbon substituent. These are skeletal isomers. Another example, the methyl ether and the ethanol. Again, as in the first example, we have to identify if they are isomers or not. And when we count the number of each carbon atom, hydrogen, and look at here, there is an heteroatom, oxygen, they are the same number. And when we look the open formulas, as we see, they have different bonding pattern, but actually here the thing is not about bonding pattern, the thing is about the functional group, because there is an alcoholic group, and here there's an ether group. Thus, this is an example for functional isomers, because they have different functional groups. And what about the third example, N-propylamine and isopropylamine? And also the name tells us they are the amines. They have the same functional group, amino group, but in different position. As you see. So this is amino group attached at the end of the chain. This is why also we call it N. But here, this is a carbon chain, 3-carbon, and amino group attached at the second carbon in the chain. So thus, they are in different position, which makes these isomers positional isomers, different positions of functional groups. Tautomers. Tautomerization is the conversion of a species formed in a reaction into a tautomer. And existence of tautomers is known as tautomerism. Tautomerism. The tautomerization is the conversation between two tautomers from one to another, and it is also known tautomerism. And tautomerization occurs as a result of the displacement of a proton. Displacement of a proton. And although it is a complex concept, it's a general behavior of amino acids and nucleic acids, which are the basic building blocks of life. And also, it is a behavior of monosaccharides such as maltose, fructose, and glucose. Via tautomerization, mannose can be converted to fructose or glucose or vice versa, and it happens in our body. And here are some examples about tautomerization, which, as you see here, an enol form converted to keto form, lactam to lactim, etc. And tautomerization is pervasive in organic chemistry. It is typically associated with polar molecules and ions containing functional groups that are at least weakly acidic. And most common tautomers exist in pairs as you presented here, which means that the hydrogen is located at one of two positions. And focus here the hydrogen, because how we define the displacement of a proton. Here the proton is the hydrogen. So we can say more specifically, the most common form of tautomerization involves a hydrogen changing places with a double bond. And here we see the common tautomeric pairs and enol form to keto form. And typically, strongly favors the keto tautomer, and it happens during the conversion of maltose to glucose or fructose. Lactam to lactim form, and as you see, it's a cyclic form of amide imidic acid tautomerism in 2-pyridine and derivative structures such as nucleobases, guanine, thymine, and cytosine. And also in amido form and imidic acid form, which the latter is encountered during nitrile hydrolysis reactions. So these are the common forms of tautomers. Stereoisomers. Stereoisomers are a category of isomeric compounds that have the same molecular formula, common for constitutional isomers, and the same connectivity of atoms, but differ in the three-dimensional spatial arrangement, or by the arrangement of atoms in space or orientation in space provide the stereoisomers. The key feature that distinguishes stereoisomers is the arrangement of atoms in space, don't forget, rather than their bonding patterns or constitutional connectivity. Bonding pattern and constitutional connectivity belongs to constitutional. Stereoisomers are significant in chemistry and biology because even small differences in three-dimensional structure can lead to profound variations in chemical properties and biological interactions. Understanding stereoisomerism is crucial for fields like drug design, biochemistry, and organic chemistry. Let's look at the classification of stereoisomers. The one is the configurational. We'll talk about cis-trans isomers, enantiomers, diastereomers, epimers, Meso compounds, and conformational, which we will talk about conformers and rotamers. Starch is the main carbohydrate in the seeds and roots of plants. Cellulose, nature's most abundant organic material, gives rigidity to tree trunks and plant stems. And to look at starch and cellulose is important, is a good example to emphasize how stereoisomers is so important. When wheat or rice or potatoes are ingested, starch is consumed, which is then hydrolyzed to the simple sugar glucose, one of the compounds our bodies use for energy. And glucose is the monomer of the polymer starch. Wood, cotton, and flax are composed largely of cellulose, and complete hydrolysis of cellulose also form glucose. But unlike starch, carnivores cannot metabolize cellulose to glucose. And here is the molecular formula of cellulose and starch, which I give information in previous slides, and focus on the cellulose. The oxygen atom here joins two glucose monomers in equatorial axis, in equatorial plane, but in starch, the oxygen atom joins two rings using one equatorial and one axial bond. And this creates a major difference. And here is the difference. Cellulose and starch, as I said, both compose of the same repeating unit. It's glucose, a six-membered ring containing an oxygen atom and three alcoholic groups, and the two monomers joined by an oxygen atom. It's a kind of oxygen bridge, which we call it privately glycosidic bond, an afer type of bond. And they differ in the position of the oxygen atom joining the rings together. Thus, starch and cellulose are isomers because they are different compounds with the same molecular formula. And they have their difference in the three-dimensional arrangement, which makes them stereoisomers. Cellulose is composed of long chains held together by intermolecular hydrogen bonds, thus forming sheets that stuck in an extensive three-dimensional network, as you see here. So this means the linear different cellulose molecules bind each other with the hydrogen bond, as you see here with the dashed lines, to provide or to form a large 3D network, large 3D network. And the axial and equatorial ring junction in starch, look at here the starch, the spherical and the axial and equatorial ring junction in starch creates chains that fold into a helix structure. Moreover, the human and animal digestive system contains the enzyme necessary to hydrolyze starch by cleaving its axial carbon-oxygen bond, but not an enzyme to hydrolyze the equatorial carbon-oxygen bond in cellulose. So, although they carry the carbon-oxygen bonding, or although they carry the glycosidic bonding, due to their molecular shape, there is a species differences, or the organism requires different enzymes to catalyze the hydrolytic cleavage of these bonds, which the carnivores does not have. So, an, an apparently minor difference, however, it provides a major difference in terms of molecular structure, confers very different properties on starch and cellulose. Chiral and achiral molecules. Everything has a mirror image. What is important in chemistry is whether a molecule is identical to or different from its mirror image. And look at here. Some molecules are like hands. Left and right hands are mirror images of each other, but they are not identical. If you try to mentally place one hand inside the other hand, you can never superimpose either all the fingers or the tops on and palms. To superimpose an object on its mirror image means to align all parts of the object with its mirror image. With molecules, this means aligning all atoms and all bonds. And the molecular object that is not superimposable on its mirror image is said to be chiral. This means our hands are chiral. Other molecules are like socks. Two socks from a pair are mirror images that are superimposable. And here you see the mirror images of two socks, and one sock can fit inside another, aligning toes and heels and tops and bottoms. A sock and its mirror image are identical. A molecular object that is superimposable on its mirror image is said to be achiral. So in nature, there are molecules which are chiral and achiral. Let's determine whether three molecules are superimposable on their mirror images. That is our water molecule, bromochloromethane, and bromochlorofluoromethane, chiral or achiral. And to test chirality, draw the molecule in 3 dimensions, draw its mirror image, and try to align all bonds and atoms. To superimpose a molecule and its mirror image, you can perform any rotation, but you cannot break bonds. This means trying to rotate the molecule in any direction, we should try to align. If you achieve to align, it's a chiral. If not, it's a chiral molecule. And don't forget, you cannot break bonds. And here's the two examples with the achiral molecules. The water, look at the water and its mirror image, and simply the bonds and atoms align. The water is achiral. And also in bromochloromethane, by rotating the bonds to align the molecule, we can achieve the bonds and atoms align. And thus bromochloromethane is a chiral molecule. So their mirror images are superimposable, which makes them a chiral molecule. But look at the bromochlorofluoromethane, which is a chiral molecule. As you see, the A and B, which each color represents the different atom, despite being trying, you can try almost infinitely, you will not achieve align the molecule completely. As you see here, these atoms do not align. So this means bromochlorofluoromethane in A and B, their mirror images are chiral because they are not superimposable, because they have a different arrangement in space or different orientation in space, of which means the bonding of fluorine, and brom are at a different arrangement in 3D space. And these stereoisomers are also called enantiomers. Sorry for my writing style. I'm trying to write using my mouse. Enantiomers. which we will define them in the later slides, and also we will do some examples. If four different atoms or groups of atoms are attached to all valences of a carbon atom in a carbon compound, such carbon atoms are defined as asymmetric carbon atoms, or stereogenic center, or shortly stereocenter, or chiral carbons, or chiral center. This is so important. But also we will look, there is a difference, and actually there is a little, maybe not little difference between stereogenic and the chiral definition that we will look later. But we can omit from now, we can use all of them. If we have a carbon atom in sp3 configuration, which forms 4 single bonds, and if each bond formed between different atoms or group of atoms such as A, B, C, and D, we call that carbon asymmetric carbon, or stereocenter, or stereogenic center. Asymmetric carbon atoms can have two different forms with the same closed formula but different open formula. For example, like the right hand and left hand, or the picture and the image of the picture in the mirror. It is seen that two different isomers of such compounds exist, and this type of isomerism is called chirality. The asymmetric carbon atom is defined as the center of chirality. An important example of chiral molecules are amino acids. You see here, there are two amino acids, and look at here, one is at the right hand and left hand, and there is a mirror showing the D form and L form. In the D form or the L form, the difference is in the functional group is on the right and the functional group is on the left. And the carbon atom bonded to 4 different groups is called a tetrahedral stereogenic center. Remember the sp3 of carbon atom, which forms a tetrahedron, and if there are 4 different groups, we can also call it the tetrahedral stereogenic center. Most chiral molecules contain one or more stereogenic centers, and the general term stereogenic center, or shortly stereocenter, refers to any site in a molecule at which the interchange of two groups forms a stereoisomer. In summary, a molecule that is not superimposable on its mirror image is a chiral molecule. A molecule can be chiral if it contains one or more stereocenters. Yes, be careful. We define the chirality by checking the stereocenters. This is why in the previous slide I said actually they refer different things. To be a stereocenter, the thing is the carbon must be in sp3 and must form 4 single bonds with 4 different atoms or group atoms. A molecule is chiral if it does not contain an internal plane of symmetry and is non-superimposable on its mirror image. So to be chiral, the thing is there must be a stereocenter, and also there is a mass which the molecule doesn't contain an internal plane of symmetry, which we see in Meso Compounds, and the Meso Compounds carry chiral centers, but they are not. They carry stereocenters, but they are not chiral, and is non-superimposable. The other thing, non-superimposable on its mirror image. A carbon atom bonded to 4 different groups is a stereogenic center. And molecule contain Molecules can contain 0, 1, or more stereogenic centers. With no stereogenic center, a molecule generally is not chiral. With one tetrahedral stereogenic center, a molecule is always chiral. With two or more stereogenic centers, a molecule may or may not be chiral. And we look at the water molecule, which there is no stereogenic center in water molecule, thus it's achiral. Or in bromochloromethane, it's not chiral. But when we check the bromochlorofluoromethane in the present center, we said the carbon is a stereogenic center and there is only one stereogenic center, so it's a chiral. With two or more stereogenic centers, a molecule may or may not be chiral. In general, a molecule that lacks stereogenic centers is not chiral. Chirality, or the property of being chiral, is primarily associated with the presence of asymmetric carbon or stereocenters or stereogenic centers, and is not adequate, and the absence of an internal plane of symmetry or other symmetry elements. So it must be asymmetric. A molecule without stereogenic centers and without such symmetric elements is considered achiral. So the chirality arises from the overall three-dimensional arrangement of atoms in a molecule, and stereogenic centers play a crucial role in determining chirality. When there are no stereogenic centers and no other symmetry elements that would introduce chirality, the molecule is inherently achiral. And molecules that lack chirality are often superimposable, and their mirror images, and they do not exhibit optical activity, another feature that which is uh, optical activity means the molecules can divert the rotation of planed polarized light. Antichiral molecules are optically active, but achiral molecules are optically inactive. Everything has a mirror image. The fundamental question is whether a molecule and its mirror image are superimposable. If a molecule and its mirror image are not superimposable, the molecule and its mirror image are chiral. The terms stereogenic center and chiral molecule are related but distinct. Don't forget. Because in general, we omit this difference, but we know they are different. In general, a chiral molecule must have one or more stereogenic centers. The presence of a plane of symmetry makes a molecule achiral, despite being carrying a stereocenter. So the plane of symmetry is also important, or the plane of asymmetry is important. And I want to repeat it to make it more clear. A chiral center and a stereogenic center are related terms in the context of stereochemistry, but they have distinctions. To be a chiral center, also we call chiral carbon or chiral atom, typically carbon form bonds to four different substituents. This will result in tetrahedral geometry being non-superimposable and on its mirror image, making it chiral. Chirality arises from the unique spatial arrangement of the four substituents around the chiral center. And this spatial dissymmetry or asymmetry causes the chiral center to have a mirror image that cannot be superimposable. A stereogenic center or stereocenter is a more general term that encompasses any atom in a molecule which is not limited to carbon. Chiral is about carbon. When its spatial arrangement is altered, results in the generation of stereoisomers. And the stereoisomers, a change in the spatial arrangement of substituents around the stereogenic center, can lead to the creation of different stereoisomers, enantiomers, diastereomers, etc. So while chiral centers are a specific type of stereogenic center, other elements like double bonds with a different substituent on each side can also serve as a stereogenic center. In summary, a chiral center is a specific type of stereogenic center. All chiral centers are stereogenic centers, but not all stereogenic centers are chiral. Stereogenic centers can include various types of atoms, and they play a role in determining the stereoisomerisms of a molecule, which can encompass both chiral and non-chiral stereoisomers, such as diastereomers. Let's do some examples. Yes, here as you see, we have a molecule, a carbon molecule carrying iodine, fluorine, bromine, and chlorine, which is the name is bromochlorofluoroiodomethane, which the carbon is stereogenic center because it's in sp3, forms 4 single bonds, which are the sigma bonds, with 4 different atoms. This is the atom A, B, C, and D, which makes it stereogenic center. And this is another organic compound, which is a 3-bromohexane. And as you let's analyze the all carbons one by one, as you see here. So to identify the number of stereocenters in a given compound, you have to check each carbon one by one. But it's very easy to understand these carbons, and also these are not stereocenters because they have multiple identical atoms, as you see, 3 hydrogen, 2 hydrogen, 2 hydrogen. But here, this carbon bonded to 4 different atoms or group of atoms. So during analysis of a carbon atom, whether it's a stereocenter or not, so break the bond and look what will remain on your hand. Don't focus on this carbon because when we break the bond here, we have this group remain. And also here at this group, and hydrogen atom and bromine, as you see, it fits to our pattern A, B, C, D, different atoms or group of atoms, which makes only this carbon a stereogenic carbon. And also look at these examples: propoxyphene, ephedrine, and the fructose. And the propoxyphene and ephedrine, as you see, each has 2 stereogenic centers, and in fructose apoptose, as you see, there are 3 stereogenic centers. And propoxyphene is a synthetic opioid analgesic medication used to relieve mild to moderate pain. Ephedrine, another medication and also stimulant that belongs to a class of compounds known as sympathomimetics. And the fructose is a monosaccharide. It's a fruit sugar. And as you check the molecules, they carry many carbon atoms in their structure. Also, these are the carbon, carbon, carbon. As you see, there's a carbon. There are too many carbons, but only 2 carbons in propoxyphene and the ephedrine, and 3 carbons in fructose are the chiral carbons, are the stereogenic centers. Stereogenic centers. Stereogenic centers in cyclic compounds. Stereogenic centers may also occur at carbon atoms that are part of a ring. To find stereogenic centers on ring carbons, always draw the rings as flat polygons and look for tetrahedral carbons that are bonded to four different groups as usual. And this is important to talk about the stereogenic centers. We have to look the carbon atoms that which are in sp3 hybrid model. sp3 hybrid model. Each ring carbon is bonded to two other atoms in the ring as well as two substituents attached to the ring. When the two substituents on the ring are different, we must compare the ring atoms equidistant from the atom. Let's look at these examples to identify whether the carbon, which is a member of a ring structure, is stereogenic or not stereogenic. And here's an example, methyl cyclopentane. And so the question is carbon 1, here carbon 1 is a stereogenic center? And all rules are applied, and the first one is it must be in sp3. This means forms four single sigma bonds. It happens there. And then we should check whether the all bonds are formed to different atoms or atoms of groups. And here an hydrogen, a methyl group, and in a ring structure follow this way. There is a carbon and following the molecule, and from the upper side another carbon and following the molecule. And to diagnose, draw a line which separate the ring structure into two same pieces, and then analyze the pieces whether they are different or not. And as you see here, they are identical groups, so equidistant from carbon 1. It must be equidistant from carbon 1, and carbon 1 is not a stereogenic center in methyl cyclopentane. What about the other carbons? As you see, there are two hydrogens for each carbon, which provide a symmetry plane, thus they are not stereogenic centers. So, what about this molecule? Is carbon 3 a stereogenic center or stereo center? The molecule is 3-methyl cyclohexene, and as we did in the first example, equidistant from here the carbon 3, divide molecule into two pieces and analyze each part. As you see, they are not identical, they are different, which makes carbon 3 a stereogenic center. Another bigger and more complex molecules carrying various numbers of carbon atom in their structure, but not all are stereocenters, only the ones having the stars that you can analyze one by one by pausing the video. They are the stereocenters, and this is the sucrose, the table sugar, and Taxol, an anti-cancer agent, a powerful chemotherapy drug used primarily to treat various types of cancer. And it works by inhibiting the growth and division of cancer cells. And you see there are many stereocenters, both in the cyclic part of the molecule and also in the linear part of the molecule. Cis and trans isomers. After defining the chirality, and stereogenic center concept, we are ready to look the type of stereoisomers and start with the cis-trans isomers. It's a spatial isomerism. It's a geometric isomerism, because to be to talk about the chirality or stereocenter, there must be a sp3 hybrid carbon atom, or there must be a tetrahedron carbon. But in cis-trans, there it's a feature of carbon-carbon double bonds, or it's a feature of positioning of substituents into two different directions, such as right, left, or upward, uh, downward, or bottom, or upper. Cis-Trans Isomers occur when atoms or groups are arranged differently around a double bond or in a ring. And these are also called geometric isomers. In double bonds, if the substituents on the carbon atoms participating in the formation of the double bond are on the same side, it is called cis form. Cis means on the same side. If they are on different side, it is called transform. And trans means on opposite sides. And they form two different molecules with different structures and different energy levels. And geometric isomers have different spatial arrangements but retain the same connection, just the direction. Same side, opposite side. Cis form, trans form. So in giving the molecule name, we have to use the cis or trans as prefix. Cis or trans as prefix to represent which isomer we have. And here the example, look at the cis-butene and the trans-butene. The substituents are on the same side here, the methyl groups, but in trans-butene they are at the opposite side. And these, and also another example, oleic acid and the allylic acid. These stereoisomers, they are the geometric isomers, they are the cis and trans isomers. And count the number of carbon atoms, oxygens, and hydrogens. They are same in closed formula, but when we open the formula, they have a double bond, and due to rotation, they are at the same side, these substituents, or at the molecule, at the side of carbon-carbon double molecule. The molecule actually bends. If we open the chain, we will see a bending like an L shape. But in allylic acid, when we look upon the molecule, it's a linear type of molecule due to the position, due to the opposite position of substituents in trans configuration. And they're so important. Oleic acid is a highly valuable fatty acid for organisms, for humans, especially for humans. But it's trans isomer, which is rarely found in nature, and it's not a valuable. And on the other hand, also we can say it's a kind of harmful fatty acid. It's a trans fatty acid. And this is a cis fatty acid, which is the valuable one, which is the essential one, especially for the cell membranes. Geometric isomers in the ring system, in biochemical terms, in rings having 5 and 6 carbon atoms or 6-membered rings, substituents lie in the vertical plane above or below the ring. According to a ligand, if another ligand is on the same side, the cis position arises. If on different sides, a trans position arises. And to refer the cis and trans positions, or to refer they are on the same side, for example, this is close to us, we use a thick line, and if we want to express it is towards us, we use the dashed line. So this tells us they are at the same side. Here they are at the opposite side. This is trans 1,2-dimethylcyclopentane, and this is cis 1,2-dimethylcyclopentane. So same molecular formula, same name, but different prefixes. So they are the stereoisomers. They are the cis-trans isomers. They are geometric isomers. Enantiomers. Two molecules, one of which is an image of the other, are isomers. These are known as enantiomers. Enantiomers, also known as optical isomers, and they are mirror image stereoisomers. But mirror image, but they are not superimposable. In other words, Enantiomers are stereoisomers that do not overlap with the mirror image, non-superimposed. And enantiomers contain one asymmetric carbon, one stereocenter. And so they show chirality. They carry chiral carbon. And the good example here is bromochlorofluoromethane. Why we call them optical isomers? Because they are optically active. They are optically active. So they rotate the plane polarized light. But when we compare A and B here, which are the enantiomers, the angle of rotation is same, but opposite. Such as if one turns into the right direction, the other in the left direction. But chemically or biologically, the enantiomers often have opposite activity or different activity. Diastereomers. Diastereomers are stereoisomers that are not mirror images of each other. In enantiomers, they are mirror images. The situation is more complex for compounds with two stereogenic centers, two or more, because more stereoisomers are possible. Moreover, a molecule with two stereogenic centers may or may not be chiral. But for the molecules carrying one tetrahedral stereogenic center, they are always chiral. So there is a very basic, simple equation about the calculation of number of stereoisomers in a given molecule. For n number of stereogenic centers, the maximum number of stereoisomers is 2 to the power of n. When n is equal to 1, so the number of stereoisomers are 2. 2 to the power 1 gives 2. With one stereogenic center, there are always two stereoisomers, and these are the enantiomers. When n is 2, 2 to the power 2 gives 4. With two stereogenic centers, the maximum number of stereoisomers is 4. Although sometimes there are fewer than 4. A molecule with two stereogenic centers can have a maximum of 4 stereoisomers, as I said. This is a consequence of the different combinations of configurations for each stereogenic center. And the possible stereoisomers are follows. Let me draw for you. So there may be an RR, which means rectus rectus, or the right. So this means both stereogenic centers have the rectus configuration, or at the right side. RS, which means one is at the rectus configuration and the other is in the sinister, the left configuration, RS. And also there are another possibility, sinistra rectus and sinistra sinistra. And these combinations give rise to the maximum of 4 possible stereoisomers for a molecule with 2 stereogenic centers. However, it is important to note that not all molecules with 2 stereogenic centers will have all possible stereoisomers. In some cases, due to the molecule's symmetry or specific arrangement of substituents, some stereoisomers may be identical or not exist at all, resulting in fewer than 4 stereoisomers. So the actual number of stereoisomers will depend on the molecule's structural characteristics. Let's look at here. To compare A and B, C and D, and also A and C, and B and D. So assume here is a mirror and compare the A and B. So firstly, we have to identify whether they carry stereocenter or not. And it's easy for now, in my opinion, because we discussed these 2 points, these 2 carbon atoms here are the stereo centers, these 2 carbon atoms in all molecules. And also when we count the number of carbons, hydrogens, and the oxygen, also they have the same number of carbon atoms, so they are isomers. They have the same bonding pattern. There's no structural difference, so they are, but there are difference in orientation, which makes them stereoisomers. And here there are 2, so this means their mirror images may be non-superimposable, may be superimposable. They may form enantiomers, diastereomers, etc. And when we look at the A and B here, A and B, we can easily say they are the mirror images having the stereocenters. So, and also similar to the C and D, look at they are the mirror images, so they are enantiomer pairs. But compare A and C or B and D, they are diastereomers. They are diastereomers because they are not mirror images. They are not mirror images. And another example here, comparing the 2 enantiomer of glucose and diastomers of glucose, which is the galactose. So in the previous slides, we talked about D and L forms for the amino acids, and also there are D and L forms of glucose. And here the D glucose and the L glucose, and they are the enantiomers. And look at the pattern of functional groups RRSR, but here SSRS. This is D and L glucose. In general, a structure with n stereocenters, we know the formula, the basic formula, 2 to power n, to calculate the number of stereoisomers. We are not considering for the time being the stereochemistry of double bonds that will come later. That we did before, sorry. For example, let's consider the glucose molecule here in its open chain form. This is the Fischer formula actually. And there are 2 enantiomers of glucose, that is the D and L glucose, which the D enantiomer is the common sugar. So we can metabolize the D enantiomer, not the L enantiomer, because we have the enzymes to get the D glucose as a substrate, not the L. And due to there are 4 chiral stereocenters, and also I know it's an optically active, so it's a chiral. So the possible number of stereoisomers is 2 to n, means 2 to the power of 4 is 16 stereoisomers possible, so including D glucose, L glucose, and the others. In L glucose, all of the stereocenters are inverted relative to D, as you see here, RRSR, SSRR pattern. So, as I said, there are 16, and you see the 1. So we have the 2 isomers of glucose here, D and L glucose, that leaves 14 diastomers. So 2 are enantiomers, the other ones are diastomers. And there are molecules in which at least one, but not all, of the stereocenters are inverted relative to the glucose. And one of these 14 diastomers, a sugar called the D-galactose. And D-galactose, one of 4 stereocenters, is inverted relative to D-glucose. Look at here. This is the difference here. RSSR. And diastomers, which differ in only one stereocenter, as seen in between D-glucose and D-galactose. This is a special type of stereoisomerism called epimers. It's a subtype of diastomers. because only they have the difference only in one carbon. This is R rectus, this here is the sinistra. So D-glucose and D-galactose can therefore be referred to as epimers as well as diastomers. Epimer is a type of diastereomerism. Meso compounds. Meso compounds are achiral compounds that have more than one chiral center. This is why in the previous slide, I especially try to explain the difference between stereocenter and chirality, because to be a chiral, there is a mass switch, they must be optically active, and there must be no plane of symmetry. They are superimposed on the mirror image and optically inactive, but they have stereocenter. As a meso compound, a meso compound must contain two or more identically substitute stereogenic centers. It also has an internal symmetric plane that divides the compound into two. What this means here is that when we have an inner plane that divides the compound into two symmetrical sides, the stereochemistry of both the left and the right side must be opposite to each other, and therefore they are optically inactive. And ring compounds can also be meso. And these two halves reflect each other by the internal mirror. The stereochemistry of the stereogenic center is constant. Meso compounds can be found especially in compounds with more than one chiral center, and their internal symmetry resets the optical activities of their enantiomers. This refers to a situation where meso compounds are sometimes optically inactive, but they contain the stereocenters. Meso compounds can be found in carbohydrates, amino acids, ring compounds, and other classes of organic molecules. However, the properties of these compounds do not require their classification by a general chemical group. They are the result of specific structural arrangements. And look at here, we have two examples, and in the left part here, as a plane of symmetry, when we put it a mirror, assume that we put a gauss mirror, the horizontal plane going through the red line of, and therefore is a chiral. Thus, this is a meso compound, despite being carrying stereocenter. But when we cut the molecule into two pieces at the center, as you see, they are identical. So this is a plane of symmetry. And note that there is a ring structure here. If we divide the molecule into two pieces, despite having a chiral centers here, or the stereocenters, these are meso compounds. Another class of stereoisomers, conformational isomers. Conformational isomers, also known as conformers or rotational isomers or rotamers, are stereoisomers that differ only by the rotation of single bonds. About the rotation of single bonds. The rotation results in different spatial arrangements of atoms but does not alter the connectivity of atoms. A molecule can have many conformations due to rotations around the sigma bond. Different structures formed by rotations around the bond are called conformers or rotamers. And common examples include different conformations of simple organic molecules such as affine, staggered, and eclipse conformation. And by the way, as an additional information, I also would like to say conformers encompass all possible spatial arrangements of atoms in a molecule due to bond rotation. while rotamers are a specific type of conformer associated with the rotation of a specific single bond, leading to different positions of substituents. In detail, this means the rotamers and conformers are different. In conformers, it's about the possible spatial arrangement of atoms in a molecule, but in rotamers, it's about a specific type of conformer associated with the rotation of a specific single bond. Rotamers are often encountered in more complex organic molecules with specific groups attached to the rotatable bond, and they may involve an energy barrier during interconversation due to steric hindrance. Conformers, including rotamers, play a significant role in understanding the 3D structures and behaviors of molecules. And here, this is a graphic, the rotational barrier in ethane as a function of the heteral angle. And the barrier to rotation in ethane is about 3 kilocalorie per mole. And as you see, there are two forms of the ethane, the staggered and the eclipse and interconversion. And conformational isomers are isomers that have different spatial arrangements of atoms in the molecule without changing the chemical structure of the molecule. These conformational isomers alter the spatial structures of the molecule without breaking chemical bonds and forming new ones. And they are commonly encountered in organic molecules and can influence the energy levels and the chemical reactivity of molecules. And here look at the energy level, a difference, 3 kilocalorie per mole. And in this example, as you see the molecule ethane consists of a simple chain where two carbons are connected and hydrogen atoms revolve around them. And the conformational isomers of ethane include, as you see here, the eclipse conformation and the staggered conformation. In eclipse conformation, carbon atoms and hydrogen atoms are in the closest, look at the red one of hydrogen, closest possible position, potentially leading to steric clashes. But about in staggered conformation, carbon atoms and hydrogen atoms are positioned as far apart as possible. Here, look at as far apart as possible, minimizing the energy level. And conformational isomers are important concepts, especially in understanding the energy and chemical behavior of molecules. Physical properties of stereoisomers. Two enantiomers have identical physical properties such as melting point, boiling point, solubility, except for how they interact with plane polarized light. What is plane polarized light? Ordinary light consists of electromagnetic waves that oscillate in all planes perpendicular to the direction in which the light travels. Passing light through a polarizer allows light in only one plane to come through. This is plane polarized light, or simply polarized light, and it has an electric vector that oscillates in a single plane. And here's a polarimeter. A polarimeter is an instrument that allows plane polarized light to travel through a sample tube containing an organic compound. And here is the sample tube, here is the light source. And we can observe the plane here, and also there is a rotation. There is a gauge that we can observe the angle of rotation. After the light exits the sample tube, an analyzer slit is rotated to determine the direction of the plane of the polarized light exiting the sample tube. So there are two possible results, right or left, and angle. About the type of It's about the molecule inside the sample tube, whether achiral or chiral, knows if it's chiral, which isomer, which enantiomer or diastereomer, or which enantiomer, which diastereomers. But in general, the possibilities are we can observe the angle is changed or not changed. So this is about optical activity. Compounds that can change the plane of polarized light pass through them or their solution are called optically active compounds. In achiral compounds, the plane of polarized light does not change. It's not optically active because it does not change the plane. Chiral compounds change the plane of polarized light at a certain angle, so rotation is seen. Therefore, they are optically active compounds. So substances that rotate polarized light are optically active. So here is the diagram showing what happens if we put a chiral compound into a sample tube. It is a light source in which there is an ordinary light oscillating in all direction, but when we put a polarizer, which will provide us the plane polarized light, and when we put the sample on the tube, if it is an achiral compound, the light exits the sample tube unchanged. There is no rotation in the plane polarized light. So this is optically active. As we can say, we have a chiral compound. With chiral compounds, the plane of the polarized light is rotated through an angle of x. There's a rotation. And is measured in degrees. A compound that rotates the plane of polarized light is an optically active compound. And look at here the rotation. The rotation of polarized light can be in the clockwise or counterclockwise direction. If the rotation is clockwise, the compound is called dextrorotatory, and the rotation is labeled italic D or plus in parentheses. If the rotation is counterclockwise, the compound is called levorotatory, and the rotation is labeled italic L, small letter L, also small letter D in italic style, and or minus in parentheses. Levo means left, dextro means right direction, right or left. Although enantiomers show different chirality, they show the same properties in terms of melting, bowling, densities, and many spectroscopic data, and cannot be easily distinguished from each other by physical methods. Two enantiomers rotate plane polarized light to an equal extent or to an equal angle of rotation, but in the opposite direction. This is the difference. What about diastereomers? Diastereomers are not mirror images of each other. We know, and as such, their physical properties are different, including optical rotation, both direction and angle of rotation. And here is an example. As you see, the stereoisomers of tartaric acid, the A, B, and C. And here, A and B are enantiomers, but AC and BC are diastereomers. Put here mirror and assess the molecule. And look at the melting point, solubility, and this is the angle of rotation and the direction. and also their designation enantiomers type, and T and L. This is the designation for the optical activity Dexor laboratory. And compare the A and B, whether they are the enantiomers, the same melting point, the same solubility, same angle of rotation, but different direction. This is the difference. But what about C, which A and C, B and C are not enantiomers? Its melting point, solubility, and others, which all are different. And even look at here, is not optically active. Divide the molecule into two same pieces, and then as you see, it's a meso compound. They are identical. These two pieces are identical, so this is not optically active, despite having stereo centers, not optically active. And what about A and B? If we prepare a mixture of A and B in the same concentration, one A and one P, one B, not P, sorry, as you see, they neutralize each other in terms of rotational polarized light, and they are optically inactive. And these are called racemic mixtures. Mixture, and it's not easy to get a one type of or to separate a one type of enantiomer in a given solution. It's not easy. What about chemical properties? When two enantiomers react with an achiral reagent, they react at the same rate. But when they react with a chiral, they react at different rates. Two enantiomers have exactly the same chemical properties except for their reaction with chiral. Let's start here. This is very important. For an everyday analogy, consider what happens when you are handed a chiral object like a pen and the chiral object like a right-handed glove. Your left and right hands are enantiomers, but they can both hold a chiral pen in the same way. With the glove, however, only your right hand can completely fit inside it, not your left hand. And a living organism is a sea of chiral molecules, enzymes, receptors are chiral. So the type of molecules interact or use in body is so important. The molecular shape determines the fate of the molecules, determines the function of the receptors or enzymes, etc. It is also important for drugs. Many drugs are chiral, and often they must interact with the chiral receptor or the chiral enzyme to be effective. An enantiomer may be effective in treating disease, but mirror image may be ineffective. One enantiomer may initiate one certain type of biochemical reaction, but its mirror image may cause a completely different response. The differential metabolism of D and L isomers by enzymes is the central principle of all metabolism. So this is so important. Look at these two drugs, ibuprofen and the fluoxetine. Each contain one stereogenic center and thus exist as a pair of enantiomers. So these are they can have enantiomers, which only one of which exhibits the biological activity. So here, this is the S ibuprofen, this is the R fluoxetine. And by the way, they are not enantiomers. I mean, there is also an R-ibuprofen and there's S-fluoxetine. And S-ibuprofen is the active component of the anti-inflammatory agents, and R is the active component as an antidepressant. And there is a two molecule showing the both enantiomers of naproxen, S and R. And this is maybe the best example here. Look at the S-naproxen. It's an anti-inflammatory agent, while its R enantiomer, R naproxen, is a toxin. It's a liver toxin. So changing the orientation of two substituents to form a mirror image can thus alter biological activity to produce an undesirable side effect in other enantiomers. It's a good example. As S-naproxen is an anti-inflammatory agent, but the R-naproxen is a liver toxin. The liver toxin. Another example is about the thalidomide. Thalidomide is which was historically prescribed as a sedative and anti-nausea medication, is notorious for causing birth defects when taken during pregnancy. And you can check my website. There's an article about the chiral molecules, which the thalidomide is given as a good example, which is prepared by one of my students in the previous years. And there are two enantiomers of thalidomide, which the one is responsible for the sedative effects, while the other is responsible for the teratogenic effects, which lead to birth defects or abnormalities in baby. If a chiral drug could be sold as a single active enantiomer, it should be possible to use smaller doses with fewer side effects. Many chiral drugs continue to be sold as racemic mixtures. However, because it is more difficult and therefore more costly to obtain a single enantiomer, and racemic mixture composed of dextrorotatory and levorotatory forms of a compound in equal proportion. Remember the previous slides that we have touched on as the example, showing A plus B 1:1 ratio, which are not optically active. An enantiomer is not easily separated from a racemic mixture because the two enantiomers have the same physical property, except the direction of rotation of plane polarized light. And recent decisions of the Food and Drug Administration, USA, have encouraged the development of racemic switches, which were originally the patenting and marketing of a single enantiomer sold as a racemic mixture. Enantiomers and the sense of smell. Research suggests that the odor of a particular molecule is determined by its shape, then by the presence of a particular functional group. For example, hexachloroethane and cyclooctane have no obvious structural similarities, but they both have a camphor-like odor, a fact attributed to their similar spherical shape. And each molecule binds to spherical shape olfactory receptors present on the nerve endings in the nasal passage, resulting in similar odors. And camphor is a colorless to white crystalline solid with an odor like mothballs. It is used in making plastics, paints, moth repellent, and in flavorings and pharmaceuticals. And here's an example. Cyclooctane and other molecules similar in shape bind to a particular olfactory receptors in the nasal passage mucus. And so these bindings result in a nerve impulse that travels to the brain, which interprets impulses from particular receptors to the specific odor. And so the molecules having the similar shapes will cause the similar sense of smell. Because enantiomers interact with chiral smell receptors, some enantiomers have different odors. There are a few well-characterized examples of this phenomenon in nature. For example, S-carbon is responsible for the odor of caraway, whereas R-carbon is responsible for the odor of spearmint. Look at here, this is the R-carbon and this is the S-carbon. And R-carbon has the odor of spearmint, and this is the S-carbon caraway. So they are stereoisomers, they are enantiomers of each other. They are both terpenoid compounds and represent mirror image isomers of the same molecule carbon. The main difference between the two is the spatial arrangements of the functional groups in their chemical structure, which affects their optical activity. And in the R carbon, which is the one of the enantiomer, it is also known as, instead of R, we can use plus. This is declaratory. It has a sweet and minty odor and is commonly found in various natural sources, including spearmint, oil, and dill. Also, it is used in the food and fragrance industry to impart a minty or sweet flavor and aroma. And it is dextrorotatory, meaning it rotates plane polarized light to the right. And the S carbon or S enantiomer, which is levorotatory, minus in parentheses, it has a slightly different odor and is commonly found in caraway seeds and some other plant sources. And S-carbon is used to give a characteristic flavor and aroma to rye bread and other food products. And it is levorotatory, as I said, means rotates plane polarized light to the left. The enantiomers R-carbon and S-carbon, as you see, have the same molecular formula. You can count the number of hydrogen and oxygen atoms and carbon atoms as well, but they differ in their three-dimensional arrangement. They are chiral compounds and do not superimpose on each other, making them enantiomeric isomers. The distinct odors and flavors they impart to various products are due to their different spatial arrangements and optical activities, and this provides a different reactions in organisms or response by organisms. My dear friends, we finished the topic, and here in this slide you see a better representation of all type of isomers we discuss in the scope of topic. The isomers we divide into two: constitutional and stereoisomers. And we look to skeletal, functional, positional, and tautomers in constitutional isomers. In stereoisomers, two main type: configuration and conformational. In the configurational, we look to Cis-Trans, enantiomers, diastereomers, and also define the epimers in under the diastereomers. I gave example for glucose and galactose, and Meso Compounds in conformational, conformers, and rotamers. And here the references I use to prepare this slide, and also for you for further study. Next topic will be introduction to organic molecules. And for biochemistry, clinical biochemistry, and more about the laboratory world, you can visit my website, so you can subscribe to or you can follow my Instagram account. And don't forget to subscribe, click on thumbs up, and open notifications for further news. See you in our next topic. Goodbye.